Welcome to a read along with Dr. Pal in the book Discrete Perspectives in Mathematics. This is section 3.3, a magic fraction. So what we're going to be doing is we're going to be taking sequences and finding nice formulas for them. But in order to do that, we take a sequence, we think of it as a polynomial, and then we're going to see what happens when we multiply that polynomial by this fraction. All right, let's take a look at an example. Let's take a sequence and turn it into a polynomial. And we're going to work in mod x to the fourth, and ignore negative powers of x, and use a kind of a tabular integration type tabular multiplication technique, as we did in previous sections where we're multiplying. So if we take our polynomial 2, 5, 10, 17, 2, 5, 17, 2, 5, 10, 17, and we multiply it by 1 minus x, so 1 minus 1, 1. So these coefficients, minus 1 is referring to the x. So when we multiply it, it shifts it over. Then we add. Notice what happens. It's like 17 minus 10, 10 minus 5. Hey, 17 minus 10 is like 17 minus 10, 10 minus 5, 5 minus 2. In other words, we get 3, 5, 7. So notice that 3 is a difference between 2 and 5. 5 is the difference between 5 and 10. 7 is the difference between 10 and 17. It's a sequence of differences of our current sequence. That's what we get. And we're ignoring and what we do, essentially what we do is, notice when we multiply by 1 over x, that shifts all our powers down, so that 3 is right at the first, and 5 is, and so forth. And then we're kind of going to be ignoring the 2. So we just kind of have that as we go along. Okay, so we get a sequence of differences by multiplying by 1 minus x and then dividing by x. And then, with the different ignoring that we have going on. All right. So, we can label that as the polynomial that corresponds to that sequence of differences as delta p, or change of p, if we like. Oh, what's this? Hey, we're looking at the sequence of differences of the sequence of differences, right? Because we're multiplying by m of x, and that's what it gives us. It gives us the sequence of differences when we multiply by m of x. Oh my goodness, see, 5 minus 3 is 2, 7 minus 5 is 2, so 2 and 2, like 3 plus 2 is 5, 5 plus 2 is 7. Oh, wow, so we have the sequence of second differences, and we can give it this kind of notation if we want, the delta with little 2. All right, so we kind of have this. Oh my goodness, if we multiply by m of x repeatedly, we're finding the different sequence of the different sequence of the different sequence n times. So think of this as being the sequence of nth differences, we'll say. All right. And the first term of this is going to be the constant term of this when we multiply it out. And that's how we engineered it, right? Because notice that the first term right here, this is when n was 2, and that happens to be the first term of that, because that's how we defined it. Oh, what's going on here? Now we're taking our polynomial and we're multiplying it by m of x plus 1. Now, this is interesting. Actually, this type of thing that we're looking at here will help us as we move forward to trying to find a nice formula for the terms of our sequence. And it's going to involve binomial coefficients, because imagine raising this to a power. Something plus something raised to a power. That's going to give a lot of binomial coefficients, actually, and that's going to be useful in our formulation for for a formula for the specific terms of the sequence that we're looking at. So let's go ahead and see what happens if we just do that. M of x plus 1 plus p of x. So notice that m of x times p of x gives us this sequence of differences right here. But then let's add that to the original. And what happens? Well, it should make sense, because notice 2 plus 3 should give us 5, right? I mean, like 3 is the difference in here. So 2 plus 3, and we're just moving up to 5. 5 is the difference between those. So if we take 5 plus 5, we get 10. Oh, and see, 7's difference here. So if we take 7 plus 10, we get 17. And that's essentially what we're doing. We're just taking the differences and adding it to the sequence. And what it does is it just moves us forward in the sequence. Oh my goodness. So if we multiply by m of x plus 1, what happens is we've taken our sequence and we've just shifted it up. So we've just kind of moved up into our sequence further. So, all right. And so it looks like multiplying by m of x has the same effect as multiplying 1 over x, which just shifts it down. Which actually, if you look at this, you look at a little bit of arithmetic, that's actually completely true. All right. But why in the world did we do this? That's so we could use the differences and the sequence itself in order to describe this motion. All right. So, okay, it's a downshifter. All right. Okay, so let's take a look at this as we go along. Differences. Okay, so what does the constant term of this look like? All right. Well, I mean, we can expand this using binomial coefficients like this. Okay. And when we can look at the constant terms of each one of these guys. But what does it even mean? The constant term of this guy is actually, it's kind of like taking 1 over x to the n and multiplying to p of x. So you've shifted the sequence down n. So you took what was in position n and you moved it down to the first guy. Oh, so it becomes a constant term. So you take the nth term of the sequence, you move it to be the constant term, and then we're going to analyze what the constant term is over here when we do this multiplication and see what we get. So the nth term of the sequence is going to be the constant term of this multiplication. So the result of this multiplication, take a constant term, that's going to be the nth term of the original sequence. Okay, so if we take a look at that and we distribute this p of x in and we multiply it to m of x, that would give us a sequence of differences. Take the constant term there. So the first guy and the difference is there. First guy and the second differences, first guy and the third differences, and so forth, and multiply them to these coefficients and add them up, we should get a description of what the nth term is. In fact, notice that this coefficient is in terms of n itself. Oh my goodness, that's like a formula in n for the nth term of the sequence. Let's take a look and see how this looks pictorially. All right, so let's suppose we have a sequence. Let's write it out and let's take the sequence of differences. First differences, then take the second differences, then take the third differences. Now let's look at the first guys right here. Let's multiply these by binomial coefficients, add them together, and that'll be actually the formula for the nth term of the sequence. A sub n is equal to something like that. How does that work? Well, we'll see it right here. See this 2? It's actually multiplied times n to n choose 0, but n choose 0 is just 1, so that's why we just left it alone. So that's where this 2 is. So this is 2 times n choose 0, plus 3 times n choose 1, 3 times n choose 1, plus 2 times n choose 2. That's the formula for a sub n. We just found a formula for a sub n. In particular, binomial coefficients, let's think about what this is. It's like an n and a 1, so one factor in top and bottom, start at n, start at 1. Here, 2 factors in top and bottom, start at n, start at 1, going up and going down. So you have this algebraic description, you can multiply it out, and you have a nice formula for a sub n. Kind of fancy. Here's another one. What if we have this? We're adding up the first n counting numbers, starting at 1 and going up to n. That's what this is. Well, let's write out what this sequence looks like when we do it. So for the first one, so 0, 1. Okay, when n is when n is 2, then we're adding up 1 plus 2. When n is 3, we're adding 1 plus 2 plus 3. When n is 4, we're adding 1 plus 2 plus 3 plus 4, so we're getting 10. So if we do this, right, we look at the differences. Notice how we're going to 0? It's kind of nice because look, eventually, like in the last case, we eventually made it to zeros. And if you eventually go to zeros, this process will work because this sum will end. Just like up here, this sum, we got to zeros. Therefore, its sum ended. We could actually make a formula that wasn't an infinite sum. That was kind of nice. So, so if we do that, notice we get 0 times n choose 0, 1 times n choose 1, 1 times n choose 2, 0 times n choose 3, add them up, simplify. Hey, that's the formula right there. We got it just by looking at a few lines of the differences. Kind of fancy technique, but it works really well. In particular, if you have a sequence defined by some recursive formula, like you take one element of the sequence and you do something to it to get to the next one, you can do the same thing. You can list out you can use that formula to write out the first terms and find some other ones as we go along until we get zeros, and we can go for it. Now, this process only works if we eventually get down to zeros. If we expect the formula to be a polynomial formula, actually, then taking differences is almost like taking derivatives in some way, and so eventually you'll get down to zero, which is nice. So this does work often, but there are many times when it won't work. If it doesn't seem like we're going to be ever be getting to zeros, we can't use this method. However, this gives us a nice technique for finding formulas. Thanks for watching.